No, here source is moving. We are talking about radioactive source. In a compound nuclear reaction, what happens? The beam falls on a target, right? And what happens to a compound nucleus? It moves. A lot of energy is coming. It moves, and after some time, then it stops. You have to make a backing in which the compound nucleus will stop. Or if you have a very thin target, then the beam falls on it, and then after production the compound nucleus flies away, and during its flight radioactive nuclei are produced which are also moving, and from there gamma rays are emitted, and those gamma rays will be Doppler broadening. And we are talking about the effect of Doppler broadening due to the detector opening angle for such gamma rays. So basically here the detector solid angle we just talked about. So omega equal to 1 minus half of cos alpha. Maximum detector opening angle is alpha. So basically this is just omega is equal to sin square alpha by 2. So the solid angle depends on sin of alpha by 2. Remember this. Now let us talk about the Doppler broadening just due to the opening angle of the detector itself. There are other factors as well. Remember the expression for Doppler broadening is E gamma equal to E0 1 plus beta cos theta. How many factors are there? Here we have got beta, here we have got beta, and also E. So each of the variations can cause here. Okay. So if there is a variation in the velocity of the nucleus itself, which is moving, if there is a small variation, then there will be Doppler broadening, or means the energy of the gamma ray will be different. If the detector opening angle is also very large, then along with this theta in which it is emitted, you will observe a Doppler broadening. Now this theta and that theta are different. Remember, this theta is the gamma being emitted from the direction of the nucleus. Suppose nucleus is moving in this direction and gamma is emitted. Then from there it is theta. But do you understand what I am saying? What is this theta? Tell me.
ওই নিউক্লিয়াসটা যেদিকে যাচ্ছে আর গামাটা অন্য একটা ডিরেকশনে যাচ্ছে, মানে একটা অ্যাঙ্গেল ক্রিয়েট করছে অ্যাঙ্গেল।
What is this theta?
থিটাটা তো ওপেনিং অ্যাঙ্গেলটাকে বলতে
যাচ্ছে আর গামাটা যেটা যেতে এমিট করছে।
আচ্ছা, ডপলার ব্রডনিং এর থিটা কোনটা বলো? এই যে এক্সপ্রেশনটা E gamma equal to E0 1 plus beta cos theta. What is this theta?
মানে সোর্সটা যেদিকে
ভালো করে দেখো, observe carefully. This is the detector. Okay, this is my detector, and there is a reaction going on over here. This is the incident beam. Beam falls on target. The nuclei moves like this. Okay, but we are observing with respect to the beam direction. Suppose this is the direction of movement of the what? The recoiling nuclei, which are de-exciting, and from there we are observing the gamma rays. Okay, so this is the theta. This is the theta.
টার্গেটের গামা।
Okay, so this is the nuclei which are being emitted. They are moving in this direction, and during this emission, theta is basically the direction of gamma ray. Now you will say, sir, how do you know this gamma ray is emitted at this angle? Come on, I am observing this gamma ray by placing a detector at this angle, right? So this gamma ray is emitted at an angle theta with respect to the direction of the beam, or with respect to the direction of the nuclei, if the nuclei are moving in this direction. This is what I am saying. There may be gamma rays in other direction. To catch them, I have to put detector in some other direction. So don't get confused. Sometimes I will ask you, or I will try to mislead you, just like now. So you have to understand this. This is important. Now, this is not detector opening angle. What is this theta? This theta is the angle of the gamma ray emitted with respect to the beam direction or the moving direction. But where is the detector opening angle? Detector opening angle is over here. This finite angle. This is my twice alpha. You can say. So I am saying that the Doppler broadening depends on this detector opening angle. Understand? It is not the theta I am concerned about. So when I am saying this, there is a variation in theta. By variation I mean this is the variation. Theta plus minus. How you observe this? This is my detector. Okay. So there is a, suppose there is a source over here. On the gamma ray enters, there are two gamma rays, right? See, this angle and this angle are very different. This is centrally absorption, this is maximum absorption. So there is a variation in the absorption angle. You understand this thing? By this is what I am trying to say. The variation in theta. Okay, so right now just consider the variation due to opening angle theta. So delta E, these two become fixed, constant. So just cos theta plus minus this alpha, detector opening angle. And from here, by little mathematics, you will find that the angular dependence is sin theta plus minus alpha by 2 and sin alpha by 2. So basically, there is sin alpha by 2 and again sin square alpha by 2. So this means both solid angle and the Doppler broadening due to the detector opening angle, this delta E, theta, both of them depend on sin alpha by 2. So how to reduce this thing? How to reduce the effect of the Doppler broadening? Sin alpha by 2. When is it small? When alpha is either near 0 or near 180. So we have to place the detector either at extreme forward angles or backward angles. Okay, so we have considered the effect of Doppler broadening due to detector opening angle theta. Now let us consider both detector opening angle theta and the velocity beta. So this is our original expression, right? This is an approximation, not the relativistic expression for small, approximately small beta. 1 plus beta cos theta. So as I was saying, so let us just consider the variation in beta and theta only. So this is my expression. Now, previously we considered this expression, right? Due to variation of d theta. Now let us consider this expression. What is this? Basically, suppose the recoiling nuclei, from there some particle is emitted. It is possible, right? Both gamma and charged particles can be emitted from the recoiling nuclei. Now we have put the particle detector at an angle theta. Previously we were putting gamma detector at an angle theta. And if the spread in the velocity of the detected particle, let it be a proton, let it be a alpha particle or whatever, the velocity with which they will be detected, if there is a spread in it, that spread is suppose d beta, then the Doppler broadening due to the spread in velocity of the detected charged particle itself is this term. E0 cos theta d beta. Now where is this minimum? This is minimum when cos theta is
90 degrees.
right, this is minimum. But again, so this is minimum for theta close to 90 degrees. Now we are talking about charged particle. What about gamma rays? Now gamma ray, when it is emitted from a nuclei, there is no variation in its velocity, right? It always moves with c. So it is not applicable for that. Now look here. So if we are talking about charged particle, and then we say that the Doppler broadening due to spread in the detected particle is minimum if we put the detector close to 90 degree. But remember, if we put the detector close to 90 degree, then the Doppler broadening due to detector opening angle becomes maximum. So what we have to do, depending on the experiment, the beam energy, the target, right? The beam, target, projectile, their mass, charge, compound nucleus produced, the recoiling nuclei, the charged particle, its mass, and all that. Depending on it, we have to calculate these two terms, and then we have to see. Because if we choose our detector at such an angle where this becomes large, although this becomes small, then it is not good. We have to optimize. That's why I have written we have to choose theta very carefully by calculating both of these two Doppler broadening contributions. Okay, so this is very important while doing experiment. Okay, so now finally let us talk about, well, this is quite interesting, Doppler broadening and its effect on the type of reaction. What do you mean by type of reaction? I will clarify. Now you see, we have got a projectile, we have got a target, right? Normally, what is forward reaction, do you know? Depending on this mass of the projectile with respect to target, the mass, we can have both forward reaction as well as backward reaction. In a forward reaction, the mass of the projectile is lower than the mass of the target. This is what we normally do, right? But in a backward reaction, the mass of the target projectile is larger than the mass of the target itself. In classical mechanics, in class 11, you have done this center of mass problem. Remember what happens if the mass of the projectile is infinity or it is twice the mass of the target, something like that. So this is what I mean by forward and backward. Forward means projectile mass is lower than target. Backward means projectile mass is larger, much larger than target. Okay. Now see what happens. To understand this, look into this picture. This is the projectile which is coming, okay, and hits the target over here, as a result of which compound nucleus reaction is produced. Now it de-excites. During the de-excitation, the residual nuclei, it flies away in this direction. See, residual nuclei moving away. Now the detector is kept at an angle, what angle? Theta, with respect to the beam direction. Okay, this is the detector angle. Detector is kept at an angle theta. The detector opening angle is alpha. We have talked about it previously. Detector is kept at an angle theta. Detector opening angle is alpha. But look at residue. The residue is flying in its own direction. The residue is flying at an angle what? Theta plus phi. Or you can say the detector angle, if this is theta, then even with respect to this, the residue has moved even phi angle. It has moved away. And there, it emits the gamma ray. So, this gamma ray, although it enters the detector, see, it is actually emitted at an angle what? Theta plus theta prime. You understand the angle? What is this? What angle is this? Actual angle in which the gamma is emitted. You see, this is the gamma, it is emitted from here, but with respect to the compound nucleus or with respect to the detector, this detector angle, the gamma is emitted at an angle theta prime, not theta. Now, this happens most of the time. There is a spread. Whenever a compound nucleus is produced, this is one such instance where the residue is formed here, it is emitted. In other case, residue will be here. In another case, residue will be here. Residue will be here. Residue will be here. So, this is what I mean to say. Spread. So, this is the compound nuclear direction, and residue can be emitted in any directions. Right? So, this is spread. This is what I meant to say, spread. Try to understand. Now, if this target is much lighter than the projectile, that means reverse reaction, then this spread will be small. But in a forward reaction, when target is lighter, then the spread is large. So you understand? The Doppler broadening will be more in forward angle because the spread will be large. But in the backward angle, backward reaction, the spread will be small. So the Doppler broadening will be small. Why? This is because this is what is deciding the factor, phi. Phi depends on the type of the reaction. In forward reaction, phi is large. In backward reaction, phi is small. And this theta prime depends on phi. So, in the forward reaction, phi and theta prime are large. And in the backward reaction, both phi and theta prime are small. So, as a result, because they are large in the forward reaction, phi and theta prime, you see, there is a large spread in theta and beta, and this causes large Doppler broadening. But this phi and theta prime are small in backward reaction, and as a result, there is small spread, and this causes small Doppler broadening. So, this is also very important when we are trying to decide an experiment. We just don't do experiment. First, we have to think in our mind. What are the important parameters? See, I am not talking about efficiency. I am not talking about peak to total. I am not talking about energy resolution. Right now, I am talking about Doppler broadening. Why? Because even if my efficiency is large, even if my peak to total ratio is very good, and my energy, I have an HPG detector, very good. But depending on the type of the reaction, the Doppler broadening can be very large. And if Doppler broadening is large, then no matter what you have, you will not be able to identify your full energy peak. Remember, we are able to identify full energy peak given the detector has good energy resolution only if the source is at rest. But in a reaction where source moves, Doppler broadening comes into play. So we have to keep all these things into mind. So most of the time we try to minimize Doppler broadening by choosing backward reaction. This is one of the ways. But sometimes, suppose the target projectile combination has to be looked into it. Suppose I don't have the type of projectile which is very high. So in that case, I cannot do a backward reaction. Then I have to go to the forward reaction. You understand? It's not that I have got infinite possibilities of targets and projectiles. We have limited possibility, and things cost a lot. The manufacturing process, the material itself, many things have to be taken into account. So keep this in mind while we are planning an experiment. This is very important. See, Doppler broadening. So this is the basic non-relativistic, more or less, when beta is quite small. So this is the expression E gamma E0 1 plus beta cos theta, and we can talk about Doppler broadening when we have d of E beta, right? And at that time, this expression depends on number 1 theta, number 2 theta also involves the detector opening angle alpha. Again, the effect of the type of reaction, the residue here, the residue which angle it is emitted, the spread, this phi, this is also important. So the type of reaction. Next, the energy of the detected particle, beta. Then also d beta is also involved. So the spread in the velocity of the detected particle. So all of these are important. Doppler broadening.